Hello again. I hope everybody is back after our short break. It is a pleasure for me to welcome Mr. Antonio Correia on behalf of this fourth part of today's webinar on the topic of foundation systems, shallow foundations, and piles. Mr. Correia is active at the National Laboratory of Civil Engineering in Lisbon. He is an invited lecturer and a well-known researcher in his field. His main research topics are the seismic risk and structural vulnerability, as well as geotechnical design methodologies. He is doing for many years theoretical research, as well as conducting Shackle table tests on in situ tests of the seismic assessment of structures. He also developed and implemented numerous innovative numerical tools. Thank you again for your presence today, and please, you have the floor.
Thank you very much. It's a pleasure to be here. So first of all, thank you very much for the invitation to this event, and I'd like to congratulate the the European Association for Earthquake Engineering for this very important initiative. I think it's very useful to practitioners around Europe and worldwide. So the section that I'm presenting on part 5 of the second generation of Eurocode 8 is on the foundation system, which corresponds to section 9, and it is dealing with the 3 main topics. So the shallow foundations, the pile foundations, and design values and verifications. And it has one associated annex, an informative one on the seismic bearing capacity of shallow foundations. Now, in terms of the general requirements, the main principle for the foundation system is that the foundation should be able to transfer the action effects in the structure from the structure to the ground, resulting in permanent displacements which are small enough to be acceptable. And so a number of particular points should be paid attention to, among them the strain dependence and cyclic effects, which was already mentioned a little bit, the verifications using either the material factor approach or the resistance factor approach, as well as the same partial factors for the materials as they are used in the structural design. One point which was one of the previous questions was on having different foundation types in the same structure. So having using at the same type pile foundations and shallow foundations and different types of foundations in the same structure. Those are not recommended. That would imply additional requirements. So the main recommendation is to have different foundation types only if you are dealing with independent dynamic units in your system. And then the issue of the analysis and verification methods related to either the force-based approach or the displacement-based approach. Now, in terms of the design values to be used in the design and verification, in the force-based approach, we are dealing with design values of the action effects, which take into account the non-seismic action effects, as well as the design seismic action effects. And these are the ones which result of the seismic analysis and are already divided by the behavior factor. These are these may be amplified in the design verifications by taking into account the over design, which is basically the ratio of the resistance to the seismic action or the design action considered in the design of one of the members, and also an additional overstrength factor, which the two of them compose what is the capacity design considerations for the design of foundation elements and foundation systems. We also have the factor key age, which we have already seen in the previous presentations, which is related to the amplitude of the accepted permanent displacements. Now, when we are dealing with the verification of the foundation elements itself, though, so this factor is 1, For the different ductility classes, we have different values of the capacity design factors. So if we're dealing with ductility class 1, which is the lower ductility class in the structural members or the foundation elements, this capacity design is taken as 1. When we are dealing with ductility class 2 or 3, so larger ductility classes, these factors will depend on the type of structure being considered, on the type of foundation being considered. So if we have raft or caisson foundations, as well as foundation beams, which are designed to DC1, so this factor will be equal to 1.25 times the component of the behavior factor, which is related to the redundancy of the geotechnical system and the structural system. If we are dealing with isolated footings or piles which are not yielding, we again have the same factor for the capacity design when it comes to the design for overturning moment and shear, while for the vertical force it is a slightly different design and coming from what is defined, for instance, in the building part for the structural members of the building. If we are considering the design of yielding piles, then of course we are not considering capacity design for the yielding piles themselves, and so these factors become equal to 1. Now, when we go to the verification of the foundation soil capacity, on the other hand, we have different capacity design factors. So we use 1 for sliding, while we use 1.2 for the bearing capacity, which is consistent with the approach that sliding is allowed, but that it should take place before the bearing capacity failure occurs, because this bearing capacity may cause permanent tilting and is less controllable than the sliding response. Now, in terms of the foundation elements, they should be horizontally connected. And so the effects in the structure due to possible horizontal relative displacement between the foundation elements should be calculated and designed for. And the foundations should be on the same horizontal plane and using tie beams or an adequate foundation slab at the level of the footings or the pile caps to connect them, all of them horizontally. And this horizontal plane may be up to 1 meter above the bottom face of footings or pile caps. It doesn't have necessarily to be at the base level. Adequate detailing of the tie beams is prescribed, as well as a nominal axial force value for the design of these tie beams, or for the pre-design of these tie beams. Now, the tie beams may be omitted if we have a stiff ground, so if we have ground category A, or if the relative foundation displacements are considered directly in the design of the superstructure, although it is always recommended to have this type of horizontal connection elements. Now, regarding the design and verifications of surface and shallow embedded foundations, so the main principle in there is that the footings so the footings and these foundation elements should be verified against sliding failure, bearing capacity failure, and rotational failure, where failure corresponds to having unacceptable permanent displacements. Now, in what is related to sliding, so the resisting mechanisms for sliding to be considered in a footing are as before. So the friction shear at the base of the footing, the friction shear at the vertical sides of the footing, which are parallel to the seismic action if the footing is cast in place, as well as the passive earth pressure on the vertical sides perpendicular to the seismic action, which is anyway limited in a force-based approach, as we will see. Now, for the bearing capacity mechanism, we are considering the resisting vertical stresses at the base of the foundation element, as well as possible shear and normal forces on the vertical sides if the element is cast in place for the resistance to the vertical force and overturning moments. Now, in terms of the sliding verification in the force-based approach, so we have the three components that I was mentioning before. So the friction shear at the base, which is given by this expression. So taking into account the friction coefficient between the foundation element and the ground. The action effects to be considered in the superstructure, they are considered without considering sliding to compute these action effects. And we have the values of the key H factor to allow for some degree of permanent sliding displacements, which are given in this table. And so depending on the value of key H which is chosen, we should expect a different range of permanent displacements to be involved in the behavior of the foundation elements. Now, in what concerns the displacement-based approach, which is a nonlinear approach, the sliding is accepted at the significant damage or near collapse limit states if it is acceptable for the superstructure, if the level of sliding is acceptable for the superstructure, as well as to any lifelines which are connected to the foundation elements and to the structure. In the displacement-based approach, so we are computing directly the displacements, and so the key H factor is equal to 1, and the full passive resistance at the vertical sides may be activated. So it will depend on the amount of sliding that we have, and so we are not limited to this 30% value which is used in the force-based approach. Now, for the bearing capacity verification using the force-based approach, we have a combination of the forces, vertical force, shear force, moment in the seismic design situation. And in Annex E, we have the information needed to construct, or we have the definition of an interaction surface for these different generalized forces. And we are also considering the inertia forces on the ground. Otherwise, we can also use the approaches in Eurocode 7, which do not consider the inertia forces on the ground, but can be used in some of the cases. So for both the force-based approach and the displacement-based approach, so the key H factors are the same as for sliding. The inertia forces in the ground, they should be considered, but may be neglected in several cases, which are described. And in undrained conditions, we are typically using the total stresses in general, but we may also use the effective stresses if the excess pore water pressure built up is limited. In what relates to the rotational failure verification, so one of the novelties is that uplift is allowed at any limit state. And like this, we are providing some seismic protection by rocking and uplift if the permanent rotations and settlements are acceptably small. And this uplift for reasons of limiting exactly these permanent rotations and settlements, for the force-based approach, it is limited to 1/3 of the area of the contact surface. Otherwise, you are using a nonlinear approach in the displacement-based approach. For the verification of settlements, so Amir Kenya has already mentioned a little bit about this, but so we are doing this verification using the free field conditions in the low seismic action class. But we have additional foundation settlements that should be considered for the moderate and high seismic action classes. And we have ground improvement if needed, or also a global resistance factor, which can be used for the bearing capacity verification related to these settlements. Now, also for the other types of surface or shallow embedded foundations, so for instance, the raft foundations, the requirements are similar to the ones for footings, it has a couple of additional requirements, but otherwise the approach is similar. And you also have several clauses on the structural design and detailing rules for the foundation elements, which are supported on the part for buildings or for bridges, but namely for buildings in terms of detailing of the foundation elements. Now, when we move into the pile foundations part, so the main principle is that the piles should be designed and shall be designed to resist the action effects that George Gazetas was discussing before. So the inertial forces and moments which are transmitted by the superstructure, and the kinematic action effects of the deformation of the surrounding ground. And these effects should be combined or considered directly together in the analysis, or combined, as George was mentioning in his presentation. And of course, we should also consider the different components of the seismic action. Now, one of the important points is that the foundation piles may develop inelastic structural deformations as long as if they are verified and detailed for that. And this is what is called the yielding piles in the code. Now, in terms of the kinematic effects, those may be neglected for small and not important structures as CC1 consequence class 1 structures, for low seismic action class, for stiff and median ground soil categories, and also when there is no strong stiffness contrast in successive layers of soil, which is described as having a shear wave velocity ratio which does not exceed 2 times in between successive layers. For the inclined piles, so bettered piles, so that they should also be designed additionally to what vertical piles are designed for. They should also be designed for the residual action effects after the earthquake due to their characteristics. Now, in what concerns the methods of analysis, so for a group of piles, there is some limitation on what is considered for the contribution of the cap base. So the contribution of the cap base and ground interface for the strength and stiffness is limited to 30% of what it would be if we had a full contact assumption. And we consider absolutely no contribution if the minimum pile spacing is smaller than 6 diameters. Additionally, in the force-based approach, we also have a limit to 30% of the horizontal passive resistance of the ground in front of the cap, as was also considered for the footing elements. For the displacement-based approach, we are looking at the analysis of the inertial and kinematic effects, which provide the maximum displacement and the displacement profile and curvature demand in the piles. We can use sophisticated numerical methods with appropriate boundary conditions, and we should also take into consideration gapping between the pile and the soil, if this is unfavorable. So the gapping tends to increase the flexibility of the system and to reduce the forces transmitted to the superstructure on one side. But in what concerns the piles themselves, it can also increase the internal forces in the pile, and it will increase its displacements. Now, for the force-based approach, we are analyzing the inertial effects to look for the forces and moments which are transferred to the top of each pile, and looking at the corresponding deflection and rotation and distribution of internal forces along the piles. We are looking at the kinematic effects to provide at least the bending moments at the pile head and at the interface between layers of different stiffness. And for the kinematic effects, it is explicitly mentioned that one may assume the seismic motion to be only due to vertically propagating shear waves for simplicity. And in pile groups, these kinematic effects, they may be determined considering a single pile in the group. Now, for the methods of analysis in the force-based approach, we should consider these several aspects. So the bending stiffness of the piles, the distribution of ground reactions along the piles, the fixity conditions at the pile head, and the pile group effects, which may be significant even if they are not for the static case. And the pile ground interaction may be represented by independent linear springs, as for the static case, with, of course, ground stiffness consistent with the level of deformation. And the lateral deflection, it may be small, and in that case, we may adopt linear elastic analysis and linear elastic solutions. And so this small deflection is defined as being either 1% of the diameter or 10 millimeters, whichever is the largest. And in the case that we have larger deflections, then we should take into account the nonlinear behavior, for instance, by having nonlinear independent PY and TZ springs, or otherwise equivalent linear strain dependent springs along the length of the pile. So some small examples which are given for an integral abutment bridge in part 2 for bridges, but which are considering the soil. So we have the integral abutment bridge here. This is the structure with the supporting conditions corresponding to the pile, which extends to the ground. And so this is a modeling example in the force-based approach, where we would have the earth impulses, the inertia forces, and so on and so forth, and with the foundation impedances being considered. In the displacement-based approach, we could have this type of modeling approach, where we are considering the soil deformability along the length of the elements, as well as the foundation deformability. And if we go to time history analysis or response history analysis, we can have the soil column represented in whatever type of modeling, but here represented with a set of springs and dashpots, which is then connected to the structure, and the pile is modeled with its corresponding impedances. Now, in terms of design verifications for the pile, so the pile system shall be designed to carry the forces transmitted by the superstructure to the pile heads, and then each pile should be designed for the combination of loading that it is taking. The design at the significant damage and near collapse limit states for yielding or non-yielding should be done avoiding any brittle mechanisms and instabilities. So for the yielding piles, we have specific detailing requirements, namely for the possible in-ground plastic hinge or the pile head plastic hinge regions. And for the yielding piles, and in order to avoid brittle mechanisms, the shear resistance of the pile itself is designed with an overstrength factor of 1.2, which is applied to the lateral bearing capacity of the soil pile system. In terms of the force-based approach, so the action effects are to be compared with the ultimate ground resistance, as in Eurocode 7. And so we have the vertical force, the shear force. For the vertical force, we have kh equal to 1, because there are no permanent displacements. For the lateral bearing capacity, instead, we have a range of values of kh, which corresponds also to a range of permanent displacements for the horizontal response of the piles. In earlier seismic codes, including the current version of Eurocode 8 Part 5, it was demanded that the piles would remain elastic after the design earthquake. However, experimental evidence and other evidence has shown that pile yielding is not as concentrated as in, for instance, columns above ground, but instead it is distributed over a much greater length of the pile due to the soil confinement. And so the plastic hinge rotation is likely small enough to have no detrimental effects on the response of the pile. And additionally, the inelastic response of piles may have a beneficial effect on the overall response of the superstructure, and this is why now we allow for the yielding piles. In terms of the design verifications for the displacement-based approach, we are looking at a comparison between the displacement demands and capacity, where the capacity in the pile is related to the plastic hinge strain or rotation limits, which are provided. So in the pile material, in the steel or reinforced concrete material. And we have a two-step verification of the yielding piles. So first one where we may express the action effects and resistance either in terms of generalized deformations or generalized forces. And so first we define the critical zones in terms of generalized forces, so where in terms of comparing the resistance and the action effects and the resistance in terms of generalized forces. But then in critical zones, we do the verification using the deformation demand against the deformation capacity with the capacity limits that are defined and subjected to the axial force in the seismic design situation. Special care is related to the piles crossing potentially liquefiable layers, where we should consider the passive type forces exerted on the pile by the moving soil layers above the liquefied layer, the kinematic constraints imposed on the pile deformation by the superstructure, the magnitude of the liquefied soil displacements, and as well as the negative skin friction in the post-earthquake situation, which is also to be considered for soil settlements in non-liquefiable soils. Now, finally, and for the final slides, I'm about to finish. So we have Annex C, which is informative. So on the seismic bearing capacity of shallow foundations, the scope of this, one of the two aims of this annex is to provide information for the calculation of the seismic foundation bearing capacity of footings, strip, rectangular, circular, and embedded foundations, where we take into account the different forces which may be acting on the shallow foundation. We compute the vertical bearing capacity as in Eurocode 7. And then the calculations are performed in terms of dimensionless generalized forces for the vertical force, the shear force, the moment, and the soil inertia forces. And the expressions allow us to have an interaction diagram for this set of forces, as is typical in structural design. Another aim or another point of the scope of this annex is to allow for the use of a global resistance factor in the foundation bearing capacity calculations, where basically we are using the same approach, but where the global resistance factor is considered in the definition of the dimensionless generalized forces. Thank you for your attention.
Thank you very much, Mr. Correia, for your interesting exposure. Now I will just go over to the question part because we have left somehow 5 minutes for it. First question coming from Christos Chrysostomus from the Cyprus University of Technology. It's regarding if we have tie beams 1 meter above the bottom of the foundation, is there not a risk of creating a short column problem?
Yes, thank you for the question, Chris. In this case, so we are talking about, first of all, 1 meter above the base of the footing, and the issue of the short column is, of course, it can be an issue, and for that reason, you have specific requirements when the tie beams are above the foundation depth, and not at the base itself. Okay, so you have special requirements, but nevertheless, this is not this issue is not as important here as it would be on the superstructure, because you always have the ground around the foundation elements, but it is considered, and you have additional requirements in that case.
Thank you very much. A further question coming from Sebastian Salamain. It's regarding Article 5.2 from the EC8, and actually a very praxis-related question regarding the situation when we have a shallow foundation and piles. Yeah, so both of them. The question is the following. The principle is taking into account the lateral stiffness of those two types of foundation and involves checking displacements. But what is the exact principle of this article 5.2?
Well, if I understand the question, the main idea is that you do not have different types of foundation elements in the same structure, unless they are dynamically independent units of the structure. And so this was written before, and this written in a slightly different way in this next generation version. I don't know, Alain, if you want to complement.
No, this is exactly what you said. It's, if you don't want to have a tie beam, or if you cannot have a tie beam, for example, in industrial facilities where the columns are separated by a long distance, then you have to take the effect in the superstructure and in the foundation in terms of differential movement of each foundation. And for that, you need to also to take into account the effect of the soil below and so on. So you can avoid having, it's not recommended, but you can avoid having tie beams, but the consequences should be taken into account.
Thank you very much. A short supplementary question.
I said tie beams, but different foundation types. Mm-hmm.
So another question, another supplementary question from the same person. It's regarding Annex F of the Eurocode 8. Yes, regarding the fact that its applicability to shallow foundations is not specified there. It is only specified for foundation stripes on one direction and not really clear. And the question is, will this annex be updated in the current version of the Eurocode?
Yes, so that was the final part that I was showing. So this annex was updated, and so now it is covering several types of foundation elements. So rectangular, isolated rectangular foundations, circular foundations, as well as the strip foundations as it was before, based on more recent research and several works on that issue. So yes, it is now more general than it was before.
Thank you. And one really last question from Mr. Professor Kostas Georgopoulos. It's regarding the fact that the concept of DC2 is changing from global plastic mechanism to local deformation capacity and local energy dissipation capacity. Is this way of thinking reflected in the coefficients used for DC2 in part 5?
So yeah, so there are two answers to this case. So first of all, part 5 is completely consistent with what was and is being developed for the other parts, and so the ductility classes, they are consistent between the different parts. Now the ductility class 2, and I could make a comparison between the different ductility classes that we have in the current version and the ones in the new version. So ductility class 1 is more or less what we have currently as the ductility class low, while ductility class 2 is a design aiming for a ductility which is not as high as the medium ductility class in the current version of Eurocode 8. And so it's in between, and this is why we are not checking for the global plastic mechanism, but we are looking instead at local deformation capacities and energy dissipation. And then you have ductility class 3, which is somewhere in between the previous ductility class medium and high. So the ductility class high was not really used in practice. It was very complex to be used. And so ductility class 3 is somewhere in between the previous ductility class medium and high. I think this is the answer.
Thank you very much again. And I will hand now over to my colleague. Thank you very much, Mr. Correia.
You're welcome.